All right, so it says an 8,700 kilogram boxcar traveling at 16 meters per second strikes a second boxcar at rest. The two stick together and move off with a speed of 7.5 meters per second. So the basis of this is you have M1 V1 plus M2 V2 equals, in this case, because they stick together, M1 plus M2 times V whatever it is. We'll call that V final. Now the second car is not doing anything, so it's zero. Do you follow that?
Something happened with my account real fast. I'm trying to fix it.
Sure. Stand by and let me know when you're ready.
Okay, here we go. All right, that was weird. It just bugged out and was like, we can't open it. And I just try it like two more times, and it's like, okay.
It works then. Great. So the mass, the first cars moving together.
Yeah. All right.
Just give me just a moment here. Put you on mute. All right, Jack. So we got M1 V1, M2 V2, but the second car is not moving, so its velocity is zero, and then they move together with that. So let's put some numbers in. I actually don't like this approach, but that is what I think students want to do. So I won't resist too much here. Um, Equals M1 is 8,700
Yeah.
plus M2, which we don't know, and then 7.5. So all I'm asking you to do in this problem is to solve for M2.
Okay.
So you're going to divide by 7.5 on both sides and subtract the 8,700.
8,700 from both sides.
After you divide by 7.5.
Okay. So 8,700 times 16. All right. So you get that. What is this? 139,200. And we're going to divide that by 7.5. I got this number. Yep. And minus 8,700. And you get that 9,860 kilograms. Is that the final answer?
Yep. So make sure that's correct before we move on to do
anything else. Yeah.
Anything else?
Correct.
All right. So I'm going to move to 7.11.
7.11. Let me check this. 7.21. This is 7.11. All right.
If you want me in a certain order, that just let me know. I'm just sort of picking the ones I see.
It's okay. Just let's get through the easy ones, and then we can focus on the hard ones.
Okay, 22-gram bullet traveling 240 meters per second penetrates a 2-kilogram block of wood and emerges going 140 meters per second. Okay, so you got a bullet traveling. Okay, you got a block of wood, and then later on, you have a block of wood with obviously the hole in it, and then the bullet's still traveling. Okay, so this is the you've got M1 V1.
Yeah.
M2 V2. Okay, so like the bullet's traveling, is the wood moving? Or is it at rest?
The wood?
Yeah.
The wood is at rest on frictional surface, right?
That's right. So it's zero, and this is a little weird, but I assume, like, the way I read this is it does not move the wood.
Yeah, to me it just sounds, well, if a block is stationary on a frictional surface when hit.
So the only thing that's moving is the mass of this bullet, which is M1.
Yeah.
At some final velocity.
Okay.
So the 22-gram bullet, the problem with that is its grams has to be converted to kilograms. You divide by 1,000 to get that.
Yeah.
240 meters per second, that's fine. That's the velocity there.
Yeah.
The mass is unchanged. See, that's not right, because hit, how fast does the move after the bullet? How fast does it move? Oh, okay. So the block does move. Okay. I made a mistake here. So that's this. So the block is m2, and it's got some final velocity as well.
Okay.
So the block is 2 kilograms. Its final velocity we don't know. We know the bullet is 22 grams. Convert that to kilograms. Its final velocity we do know, which is 140.
Okay, so we're just looking for that final velocity, right?
Yep. So this is a number. This is a number.
For this.
Yep. You get your two numbers, and then you divide by 2. It looks like.
All right. Let me get this. Sorry. So 22 divided by 1,000. All right. Times 140. Get 3.08. Okay. So 22 divided by 1,000 times 240. All right. And subtract 3.08 from that. And divide that by 2. 1.1?
Yep, 1.1 meters per second.
Okay, so the block is moving that fast?
Yeah.
Why so slow?
I mean, it depends on the velocity of the bullet, the mass. I have no idea if this is reasonable or not.
Yeah, it is reasonable, actually. That's the answer. You got it right. Alrighty. What do you want to go to next?
Let me scan through here again. So 716 looks to be our next one. Just make sure.
The golf ball, the massive blank.
Yes.
Perfect. I'm on it. Yay.
We know your thoughts down below.
Golf ball of mass 0.045 kilograms is hit off the tee at a speed of 33 meters per second. The golf club was in contact with the ball for 3.5 times 10 to the minus 3 seconds. Part A is to find the impulse imparted to the golf ball. So impulse has some sort of formula, which I don't know without looking up. If you've got it, you can tell me, but I'm gonna just I'm gonna see if I can find this question on an online resource. Looks like I have, and it'll tell me what the impulse calculation is. I don't know. Okay, the impulse, which I didn't really, I think sometimes they use J. Do you happen to know what your book uses?
J for what?
Impulse.
Impulse. I have no idea.
So the impulse is the mass times the change in velocity. So the mass here is the mass of the golf ball, which we've got at 0.045, and then the change in velocity is that it's v final minus v initial. So its final velocity is 33. Its initial velocity is 0 because it's not going anywhere. So that's it. I mean, that's what they're asking you to find. So we're gonna grab a calculator and calculate this value. I get one up here. 0.045 times 33, 1.485.
1.485.
Okay, now the units, it's a little awkward because it's a kilogram meter per second. So it's a Newton times a second.
Newton per second?
Well, it's not per, it's Newton times seconds. Let me know if that...
Kilogram per second? Oh, let me check.
We might also have a significant figures issue. It might just be 1.5 newtons.
1.5 newtons?
Newton seconds. Because your answer...
It doesn't like the formula, the way that I put it in. I just tried to multiply them, but it wouldn't let me.
So your unit is just N with an S to the side of it.
Still won't let me.
Okay.
It's so weird.
So the next part of the question is the average force, and to find this, you take the change in momentum over the time, which is your answer from the previous problem, the 1.485, and you divide it by the 3.5 times 10 to the minus 3. That ends up giving you about 158 newtons. So it says two significant figures, so 160 newtons.
160 newtons for this.
Yes.
I'm still trying to screw with the part A.
So part A, it might be kilogram meters per second. Which, I mean, I don't understand, but that's, so it might be that it's 1.5 kilograms times meter per second, which is a Newton. So I don't understand.
Incorrect. Enter your answer with a different unit.
Let me maybe I
Check
give you wrong
online.
number. It's 1.485, 1.5. Yeah. This problem with these online systems. I don't really know where to direct you. These are the right numbers. This is not the right number. No, it's 424 newtons, or I guess 420 newtons, because it says two significant figures.
There we go. All right. And now for part B, it doesn't say 160 units is correct.
It's 420. I have, this is not calculated correctly, and the it's
all right. There we go. Got both.
Yeah, okay.
Perfect. Thank you. All right. On to number 4, or whatever you want to go to next. Whatever works for you.
Okay, let me go back to 7.16. I thought I saw 721 there. That was this one's got a lot of parts to it, but we can still do them all. So I'll get this up here. So 93 kilogram fullback is running at 3.1 meters per second east and is stopped by 0.85 seconds by head-on tackle by running back. Okay, calculate the original momentum of the fullback. So that's mass. The change in momentum is mass times the change in velocity. So the mass is 93. The change in velocity, it's now this is where I don't know about so the final is 0 minus 3.1. So you want to calculate that and try it for part A.
Versus 0, so negative 0. Oh, wait, no. Negative 3.1 times 93, right?
Yeah. So then this is where you might be off by a sign, depending on it. I don't, in the direction. So I think this is negative, but
288.3. What would be the unit though?
Same as the previous problem that you
kg times meter per
Yeah.
second.
yes.
Okay, I'll put that in there, and then we'll go to this part, and boop. Maybe this will work. It says check your signs. Oh, is this it? I just want it says positive.
Yeah.
Okay, that's correct. All right, let's go to part B. Calculate the impulse exerted on the fullback.
Okay, so the force exerted by the fullback is the change in momentum. Is the change in momentum, the value we just found divided by the time. So the time is 0.85. So it's that number we just found, the 288.3 divided by 0.85. So that's about 339.
What would the unit be?
Same as from the previous problem, whatever you entered that worked.
Incorrect.
Are the units wrong?
I guess the units, yeah. No, not the units. It just says incorrect for some reason. I think that would tell me if the unit was wrong. Let me check this. I'll check online to make sure that it's that we're not putting in the wrong units or whatever. Let me just see this. Good.
It could be negative as well.
This one would be. I think it's negative. It's probably
Okay.
negative. Let me check this. All right, I'm gonna put in negative. We'll see what happens. Nope, still incorrect. The impulse exerted on the feedback.
All right, so the first one we got, the second, okay, so the impulse exerted on the fullback.
Oh, that's just 290, I think. Negative 290. Is it? Yeah, that's it. It's just negative 290. Negative from what we had last time. All right. Calculate the impulse exerted on the tackler.
So that's
okay.
the other direction. So it's positive 285. Oh, the part D is what I just gave you. Right?
This is it 339?
Yeah, part D is that.
Same units, whatever.
Yeah. Part D is in units of newtons.
330. Enter your unit using units of force. I put kg times meter per second, but okay. What's this one? It would be newtons, right?
Yeah.
There. All right. Time for C.
Part C is just the it's the positive of the answer in A.
That's it.
Yeah.
290. Perfect. All right. So that's all done. Let's go to these next problems. Thank you, Matthew.
Okay. We're up to so we did 21. 28 looks like it's next, so we'll head there. 28. Okay. So just snipping this in. All right, if one ball's initial speed was 2.2 and the other's was 4.4 in the opposite direction, what will be their velocities after the collision? Oh, I'm sorry, there is more information here. equal mass undergo a perfectly elastic head-on collision. So this was always a little bit of a struggle for me, kind of remembering the difference between elastic and inelastic. One energy is conserved, one energy is not conserved. So it's it's not always clear, but the velocities are going to, it's like, I believe they're just going to, they're going, they collide, and then they go backwards the way they came.
Oh, okay.
So because velocity accounts for direction, I guess it's going to be like minus 2.2 comma minus 4.4, because they're going to be going. Not sure though. Let me check. So it says they will interchange their speeds.
Mm-hmm.
So they simply swap. So since they swap speeds, I guess you got to go 4.4 comma 2.2 meters per second.
There we go. Negative 4.4 comma positive 2.2.
Yeah, I guess I don't understand that, because if they're in opposite directions, I mean, one of these should have been negative, but not for me to say. So, okay. So we got 28, which is 28. So now we're up to 31.
This is a 2.1, 2-part one. Let's see.
A ball of mass 0.305 kilograms that is moving at the speed of 5.1 meters per second collides head-on and elastic with another ball at rest. Immediately after collision, the incoming ball bounces backward with a speed of 3.5 meters per second. Calculate the velocity of the target ball after the collision. Okay. So there must be something else going on in this one, because like it seems like they're switching from inelastic to elastic collisions here. Okay, so I guess we don't have to make this too complicated, but you got a ball moving and another one that's not moving.
All right.
So we got a ball, we got a 0.305 kilogram ball, and it's moving with mass, or it's moving with velocity 5.1. The other one isn't moving, so it's plus 0 equals. Now this ball, which has the same mass, it's moving backwards now, so its velocity is minus 3.5.
Yeah.
Okay. It says here that since the now the other ball backwards, the target ball. So the other ball is moving, so it's got some mass, which we don't know. So we don't know its mass or its final velocity. But because it's elastic, okay, that's the key here. So because it's elastic, there's actually a simplification for this. Since it's elastic, if you have a ball that's going 5.1 to start, it breaks apart into the 3.5 5, and then the other amount has to add up to it, so 2.6 to go with it. So I believe V is 2.6 meters per second.
For part A?
Yes. That's only because it's elastic. It's elastic, so the velocities combine to be the same.
That doesn't work for part A. 2.6 doesn't.
I'm looking it over. I don't know. So let's see here. So everything I just said applies to inelastic collisions. Okay. Okay. So the kinetic energy is conserved, is what they're saying here in this. So that's a different calculation altogether. So the kinetic energy is conserved, which means that you have this 1/2 m1 v1 squared for the first ball, 1/2 m v2 squared for the second ball, but it's not moving, so that's 0. Equals, boy, oh, they do it this way. So this one, I don't even know if this is right. They combine the momentum equation and the conservation of energy equation. So they do what we did up here, and they tell you that they solve this for m v final, and then they use that in another part of this problem. Let me see what else I can help you with, because I don't feel like that's.
Found a Yahoo Answers one that I can send to you that's of a slightly different problem, but it's the same gist of it. I'll send it to you in the.
Well, it doesn't help because the numbers change so much that you're not. I mean, you've got to follow your numbers through the question. I mean, unless it's exactly the same numbers, then you can.
Well, it's not the same numbers, but at least it has like the same idea.
I'd like to move to 7.67.
All right.
Let's see if we can get this one knocked out. We'll come back to that previous one. Okay, so here you're looking at a situation where they're both at rest, but then they push together, and they're like moving away. Okay, and the significance of this problem is that I think we can do this one with conservation of energies and conservation of momentum. So, wow, this one's pretty complicated. It's strange. Okay. All right. So the conservation of momentum equation is that they start out. You've got the mass of the first astronaut, velocity of the first astronaut, plus the mass of the second astronaut, velocity of the second astronaut. But they're not moving, so those are both 0.
Okay.
Equals, you have the mass of the first astronaut times its velocity final, plus the mass of the second astronaut plus its velocity final. So the result of this is that you can solve for this relationship between the two. You can this is really V1 and V2 because they're finals. You can find the ratio of V1 over V2. If you do a little bit of math here, it ends up being, let me get the numbers right here, M2 over M1, which equals, in our problem, I can't remember. 84 over 58. Okay, so that doesn't seem to help, but if we consider that the time that it takes for the astronauts to cover a certain amount of distance, t, it's related to the velocities. So
Yeah.
if you take you got this distance equals rate times time. Well, your rate's really velocity. So time is equal to distance over r, but r is really velocity. So in your problem, it's 12 meters over the velocity that we have here. So in short, you can substitute this ratio in here, or this ratio in here, and get 12 over 84 over 58.
Over 84 over 58.
And that gives you this relative thing. They call it x in the solution. And then you take your 12 plus the x to get the final distance between them. So I don't really like that, but I mean, that's the answer. So that ends up being about 20.3 meters. Did that work?
Says no. It says enter a new answer.
Are you sure?
Yeah.
I'm looking at, does it say like two significant figures or something?
Maybe. Wait, let's see. Yeah, the two significant figures.
So maybe 20. Oh, you know, it's 11. I grabbed the wrong number. So it's 11. It's this 11 over V. So I got to adjust my numbers here. So it ends up being 18.5. So we'll call it 19 meters.
Correct.
Okay. All right.
Last three.
Say that again.
Last three.
Okay. So which ones are we lacking? Give me. I mean, I see a center of the mass of the Earth, Sun, Moon system.
7.31, 7.26, and then then the center of the mass of the Earth,
Okay.
Moon, Sun system.
I thought we did 7.26. Nope. Okay, this one I think we can do. All right, so all right, I'm gonna snip in 7.26.
Yeah.
And do part. We'll see what parts we can do here. All right, a 0.3 kilogram puck moving east has a head-on collision with a 0.9 kilogram puck at rest. Assume that the collision is perfectly elastic. What is the speed of the 0.3 kilogram puck after the collision? Okay. See if I can find a good reference here to work through this one. So do these collide together?
Let me see.
Moving east, speed of head-on. Velocity of separation is equal to the velocity of approach. So I don't understand this. They don't tell you the speed after collision, do they?
Speed after collision. No, I don't know why it doesn't.
This is something that isn't clear to me, but it has to do with collisions being elastic versus inelastic, and I'm not going to claim to be any kind of expert on that. What ends up happening here is you can like factor out some values, man. So it's something like this. You've got 0.3 times its initial velocity, which I keep losing the number. It's on there. So 0.3 times 5.44 plus plus 0, whatever the other mass is, 0.99 in this case.
Mm-hmm.
Is that the right mass?
Yeah, 0.990 kilograms.
Okay. It's not doing anything. It's 0. Okay, so it doesn't seem like it helps, but it's 0.3, and then we got velocity 1 plus 0.99 velocity 2. Okay.
Yeah.
And what we find here is that there is some like these numbers are the same over here. So we can divide everything by 0.3 is in short what's going to happen here. This is 0, so this goes to 0, but we can divide everything by 0.3.
Okay.
So we get V1 plus, and then 0.99 divided by 0.3. Okay, it's 3.3. You get 3.3 V2, and then over here you get this 5.44. Okay, so they say though that since this is scholastic, since this is elastic, okay, this is our first equation. We have V2 minus V1. V2 minus V1 equals 5.44 minus 0.
Okay.
So this, as a result, gives you V2 equals 5.44 plus V1, which you can put into this equation up here to find to solve for V1. So it's, I mean, I don't necessarily understand. I understand the equations work together, but we'll see if we can get this here. So we get 5.44 equals V1 plus 3.3, 5.44 plus V1. So you get this 3 point. So the answer here is you get V1, 3.3 V1. So that gives you 4.3 V1 on this side. 5.44 minus 3.3 times 5.44, and then you divide by 4.3. Sorry if that was not clear. I'm not sure I understand it, but
So
get a number.
4.3.
Divide by 4.3. So you end up getting 22.7. No, I'm missing a subtraction symbol somewhere. You get 2.9 minus 2.9, but it's supposed to be, and so I think the units is changing to be velocity being positive, so 2.9 meters per second.
All right, 2.9 meters.
See if that works.
Correct.
Okay,
All right,
part
C.
B. Part C is just it's 2. It's the same number.
2.9.
Yeah. And it should be in the opposite direction as, like, whatever you answered for part B, D should be in the other direction, I believe.
Oh, wait. For C, it doesn't work. 2.9 doesn't work.
Try for C, really?
Yeah.
Try negative 2.9.
Doesn't work.
Oh, I'm sorry. That's totally wrong. It's 5.44 plus that, so it's 5.44 minus 2.9. It's 2.54.
Correct.
Okay.
All right. Last two.
All right. I'm gonna take a shot at this location of the center of the Earth problem.
Okay.
Let me see if I can find a reference for what this one. The other ones were I was finding in a textbook, but this one I didn't find, or I don't see that it's got a reference to a number. Let me get it snipped in here. Oh, you can't see the other parts. Lovely. Oh, we're doing center of mass. Okay. Mass, mass the sun, distance between. Okay. So they give you a center of mass calculation in your book. It's basically a weighted average. The center of mass is the m1x1 plus m2x2 over m1 plus m2 are the weights in this case. So they give you the mass. They give you the mass of the moon, 7.35 times 10 to the 22nd. They give you its distance, the 3.8 times 10 to the 5th.
Yeah.
Okay. Sorry, I'm getting caught up here in my numbers. So they're telling you, okay, so we don't have some great numbers here. You calculate the center of the mass for the Earth Moon system. So in the first example, the x1 is 0 because that's the Earth. So it's like me m moon. Maybe that doesn't make sense. This m1 is e, so it's like me x1 plus mass of the moon x2, but x1 equals 0 in this first one. Because they're saying like, here's the Earth, here's the moon, choose that as your 0.
Are A 0?
Yeah, the x1 is 0. So it's the mass of the Earth times 0 is 0, plus the mass of the moon. So this is the 7.35 times 10 to the 22nd. And then what is our number for distance? 3.8 times 10 to the 5th. Over the mass 1. So the mass of the Earth is the 6 times 10 to the 24th plus 7.35 times 10 to the 22nd. So the answer, I'm going to punch this in my calculator. It's like 4.6 times 10 to the 3rd kilometers. See if that's going to work.
Correct.
All right, part B, I bet, asks you to switch the positions. Does it say that x equals 0 is at the moon?
Give me 1 second. I'm going to send you the screenshot of it.
Oh, we don't have time for that. So
we
just
don't? Okay.
yeah, that's just if you could just tell
Center
me that.
mass of the Earth Moon system, the radius. Select one of the answers below. The center mass is exactly in the center between the Earth and the Moon. The center of mass is nearer to the Moon than the Earth, but outside the radius of the Moon.
Yeah, I can't really answer that. Part B, the center of mass is inside the Earth. Yeah, it is inside the Earth. I heard that, right?
Correct.
Okay.
All right, part C.
So part C, I don't know what it says.
Calculate the location of the center of mass of the Earth, Moon, Sun system
Okay.
during a full moon. A full moon occurs when the blink of a blink. Use a
All right.
coordinate system in which the center of the sun is at x to 0.
Yeah, that's what I'm seeing here. So they use the it's x1 m1 plus x2 m2 plus x3 m3 over m1 plus m2 plus m3. M1 is the sun, m2 is the earth, and m3 is the moon. So this is 0. You've got these values, you plug them in, and this one shows as being 455 kilometers.
Okay.
We're pretty much out of time. So thanks, Ian Jack. Thanks for being flexible with me. We did get it all in. I'll send out these notes and screen recordings here soon.
455 kilometers?
Yeah, 455 kilometers.
Correct. Awesome.
All right. Have a great night. Thanks
Yeah.
a lot.
Thank you for your time. I'll see you
Okay.
later.
Bye now.
Bye-bye.